In Chapter 10, we're going to move from discussing characteristics of gases to discussing solid and liquid phases. Recall that the three common phases of matter, solid, liquid, and gas, can generally be distinguished from each other by these sets of features. A solid has a constant shape and constant volume, so that it retains a definite structure, and its volume can always be measured based upon that structure. Solids consist of particles at a microscopic scale that are very close together, and so there's little compressibility for a solid. Liquids do not have a definite shape. Instead, they conform to the shape of a container that they're in, but they do retain a constant volume. Particles of liquid are close together, although not quite as close as solid particles, and so liquids also have low compressibility overall. We've seen already that gases do not have a definite shape nor a definite volume. They have high compressibility because particles that make up the gas phase are far apart from each other. As we move between phases, we either input heat to go from solid to liquid to gas, or remove heat, in other words, heat is released, as we condense phases, going from a gas back to a liquid, back to a solid. We can summarize and give names to those phase changes as we transition between physical states of matter. Going from a solid to a liquid is a phase transition called melting. From a liquid to gas, vaporization. Reversing this direction, going from gas to a liquid, is condensation. From a liquid to a solid, freezing. Interchange between a solid and a gas is either sublimation, for going from solid directly to gas, or deposition, going from gas directly into solid. We could sketch a heating curve for a substance like water, as we've done several times in this course, and think about the temperature associated with the addition of heat to what initially starts out as a chunk of ice straight out of the freezer. There are going to be two benchmark temperatures, 0 degrees Celsius and 100 degrees Celsius under normal conditions, that describe changes in the phase for this chunk of ice. At temperatures straight out of the freezer, we expect ice to be much less than 0 degrees Celsius and to be in the solid state. As we start to add heat energy to that ice, its temperature starts to rise until it hits 0 degrees Celsius, the normal freezing point for water. At that temperature, as we continue to add heat energy, that block of ice sits at the same temperature, 0 degrees Celsius. And it's not until we completely transform that solid into liquid that the temperature can begin to rise once again. At 100 degrees Celsius, the normal boiling point for what's now liquid water, again we reach a plateau where added heat energy does not increase the temperature until all of the liquid water vaporizes. If we could trap that vapor and continue to add heat to it, we could continue to raise its temperature, so that at this point down here, we've got a solid. In the middle, we've got liquid. At the extreme, we've got gas. These plateaus represent a balance or equilibrium between first solid and liquid, and next liquid and gas in phase transitions. Here we represent melting. Here we represent vaporization. And any movement up this staircase requires that we input heat energy. And input of heat energy represents an endothermic process. The reverse, moving from a gas to a liquid to a solid, requires that we remove heat energy from a substance. And all of the phase transitions that condense phases are exothermic. Going from a gas to a liquid is condensation. Going from a liquid to a solid is freezing. The question that we're going to try to answer here in this chapter is, why are there plateaus between these phase changes? Why is there no temperature increase as a solid melts to a liquid, or as a liquid vaporizes, boils to make vapor? The reason for there not being any temperature change during these phase changes or plateaus is that in these regions, phase changes require energy to overcome intermolecular forces. Remember that on a particulate scale, solid particles are very close to each other. Liquid particles are also fairly close to each other, but not quite as close as solids are. To go from a solid to a liquid, we've effectively got to physically separate particles from each other. And likewise, to move from a liquid to a gas, we've got to once again further separate particles from each other on a microscopic scale. The ease with which we can separate those particles on a microscopic scale depends upon the chemical makeup of those particles in the first place. And we can discuss the chemical makeup and its effect on how difficult it is to overcome forces of attraction on a particulate scale by discussing intermolecular forces. These are forces that occur between molecules, as the prefix inter suggests. The forces that exist between individual discrete molecules are comparatively weak with respect to bonding forces. Things like covalent bonds far outweigh in energy intermolecular forces of attraction. Think about an intermolecular force as being like the force between two magnets attracting each other. Although it's fairly easy to separate two magnets from each other, it's difficult to break apart a single magnet into smaller pieces. An intermolecular force is like the force of attraction between magnets, while a chemical bond is like the bonds that make up the magnet itself. There are 5 types of intermolecular forces that are important, and in this class we're going to talk about 4. In order of decreasing strength, those 4 are forces between ions and dipoles of molecules. Hydrogen bonding, dipole-dipole attraction, and London dispersion forces. They are mapped out here in this diagram, and we're going to explore these one by one. In ion dipole attractions, the full charge of an ion, either a cation or an anion, is attracted to a partial charge on a polar molecule. We've talked briefly about partial charges on polar bonds, and given a disparity or bias in how bonds are arranged for a more complex molecule, a molecule as a whole can have regions of partial charge. So that a fully charged ion is attracted to an opposite partial charge on a molecule that we call a dipole. For a water molecule, for instance, we have 2 asymmetric bonds. A bond to hydrogen from a single oxygen atom. This oxygen atom has 2 lone pairs of electrons on it. Oxygen is highly electronegative and far more electronegative than either hydrogen atom to which it's bound. If we analyzed each bond in turn to the hydrogen on the right or the hydrogen on the left, we would say that in both cases, electrons are far more biased to be around the oxygen side of this molecule. We would point our bond polarity towards this oxygen atom from either the hydrogen on the right or the hydrogen on the left. In total, then, electrons are more likely to spend their time around the central oxygen, and so we get a buildup of electrons that spend much more of their time on this oxygen side of the molecule, rendering this side of the molecule partially negatively charged, and we indicate that with a delta minus sign. The hydrogen end, meanwhile, is collectively partially positively charged because it lacks electrons most of the time. Because there are two distinct regions, one with a positive charge on the bottom and one with a negative charge on the top, we say that this molecule as a whole is a dipole. Two polar regions of opposite charge. Now, imagine some stranger, like a sodium cation, coming close to this water molecule. As this ion of sodium and molecule of water approach each other, what we'll see is that the sodium cation likes to be near the partially negative end of this water molecule. Sodium is a fully positively charged cation, and the oxygen side of this water molecule is partially negatively charged. Opposite charges attract, and even though there's not a full negative charge on oxygen in water, the oxygen atom, by virtue of being so much more electronegative than hydrogens and being asymmetric with respect to its hydrogens, has a partial negative charge. Sodium will sit next to the oxygen side of the water molecule preferentially. Next, imagine something like a chloride anion approaching this water molecule. Chloride has a fully negative charge. This negative charge is attracted towards the region of partial positive charge on the water molecule. And what we'll say is that if we expose a substance like sodium chloride, NaCl, to water, sodium cations arrange themselves preferentially around the partially negative oxygen side of this water molecule. Chloride anions arrange themselves preferentially around the partially positive hydrogen ends of the water molecule. The reason that they do this is due to the ion dipole attraction, and if this ion dipole attraction is more preferential than the attraction between sodium and chloride ions, then sodium chloride can dissolve in water. So what happens if we just had water molecules and no sodium chloride or ions of any sort added at all? In the case where we just have polar molecules present, those polar molecules can still interact with each other. Again, polar molecules arise due to differences in electronegativity between atoms that participate in bonding and asymmetry in those bonds. For example, in a molecule like HF, hydrogen fluoride, we expect that because fluorine is so much more electronegative than hydrogen, electrons are much more biased about spending their time on the fluorine side of this bond than on the hydrogen side, and we'll call the fluorine end partially negatively charged, and the hydrogen end once again partially positively charged. Again, this is a dipole because there are two distinct regions of partial charges. Now suppose that we introduce multiple hydrogen fluoride molecules to each other. So we have three of them, and we're going to think about what these three molecules will do to organize. Every one of these hydrogen fluoride molecules has a dipole, a partially positive side and a partially negative side. When these three molecules get close enough to each other, they're not going to want to align in a way where positive and negative charges are adjacent, because like charges repel each other. Instead, it's more likely that these hydrogen fluoride molecules will align in such a way that opposite charges are next to each other, so that we get an alternating pattern of positive, negative, positive, negative. These molecules will align in such a way that opposite partial poles are attracted to each other. We call this the dipole-dipole interaction. This dipole-dipole attraction is any attraction between partially positive and partially negative charges. The partial negative charge from the fluorine side of one hydrogen fluoride molecule in this example is attracted to the partial positive charge, the hydrogen side of another. And that partial hydrogen positive charge is attracted to the partial negative fluorine side of yet another HF molecule, and so on ad infinitum. Any polar molecules experience a dipole-dipole attraction. But there's a special case of this dipole-dipole attraction that's particularly strong. This particularly strong case is called hydrogen bonding. And despite the name bonding, this isn't true bonding. It's just an appreciably strong case of dipole-dipole attractions. Hydrogen bonding is a special case of dipole-dipole interaction that, like its name suggests, involves hydrogen, and specifically hydrogen bonded to one of the most electronegative atoms from the periodic table, namely either nitrogen, oxygen, or fluorine. In the case where hydrogen is bound to nitrogen, oxygen, or fluorine, we say that the force of dipole-dipole attraction is so strong it warrants its own standalone category, referred to as the H-bond, hydrogen bond. Water is a prime example of a molecule that experiences hydrogen bonding interactions between individual water molecules. This attraction between water molecules occurs because hydrogens on one molecule are attracted to oxygens on another. And this attraction reverberates throughout the microscopic structure of water molecules themselves. And again, hydrogen bonding only ever occurs when hydrogen is bound to nitrogen, oxygen, or fluorine. Our last category of intermolecular force is one that is universally pervasive, but represents the exclusive intermolecular force between nonpolar molecules, molecules that do not have a bias or difference in electronegativity that results in a dipole. London dispersion forces are a type of van der Waals force. These are universal forces that occur between all molecules solely on the basis of those molecules having electrons that move in constant motion around the nucleus of their atoms. These are incredibly weak forces. And because of this, for many intermolecular interactions, these dispersion forces are trivial or negligible. We can say that the general trend is that these forces increase in strength as the molar mass or molecular weight of particles increases. But what's important here is that London dispersion forces represent the exclusive intermolecular force between nonpolar molecules. Fluorine, F2, is a nonpolar molecule. It's got a Lewis structure that looks like this, omitting lone pairs of electrons. Because there's no difference in electronegativity between two separate fluorine atoms, we'd say that there is no dipole. No dipole means that this fluorine molecule is nonpolar. Therefore, there's no partial positive, no partial negative side to this molecule. There's no full charge anywhere on this molecule. When two fluorine molecules get together, the only intermolecular force that could act between them is London dispersion. Therefore, two fluorine molecules next to each other really don't have a whole lot holding them together. We tend to find fluorine in the gas phase due to the weakness of intermolecular forces of attraction between fluorine molecules. Thus, we can summarize these intermolecular forces on the basis of the presence of ions, polar molecules, and/or nonpolar molecules. Should interacting ions be present? Ionic bonding, the attraction between fully positive and fully negative charges, or ion dipole attraction, the attraction between full charges and partial charges or dipoles on polar molecules, predominate in strength. If only polar molecules are present, then dipole-dipole forces predominate. In special cases, if those polar molecules contain hydrogen bonded directly to nitrogen, oxygen, or fluorine, we have a special case of dipole-dipole attraction that's particularly strong in hydrogen bonding. We have not talked about, nor will we talk about, dipole-induced dipole forces here. Thus, our last category concerns nonpolar molecules interacting with other nonpolar molecules, where only London dispersion forces dominate. Although there may be more than one example of an intermolecular force of attraction between molecules, this map summarizes the strongest intermolecular force of attraction that could be present given a particular situation. So let's put that into practice and see if we can identify the strongest intermolecular force of attraction that we would expect between molecules of particular types. So here are the molecules, ions, that we are going to consider. Firstly, what happens when sodium cations and water are mixed? In the case where we have a fully charged cation or anion with a molecule that's polar, like water, again, we can describe water with a Lewis structure that looks like this, where the central oxygen atom has far more electronegativity than the peripheral hydrogens, and so is partially negatively charged. We can describe the interaction between ion and dipole through the ion-dipole intermolecular force of attraction. We say that the strongest force of attraction that could exist between sodium cations and water is an ion-dipole force. But remove sodium cations or ions entirely from the equation, and just two water molecules interact with each other in such a way that the partial positive charge of one molecule aligns with the partial negative charge of another. This alignment of poles indicates that we must be dealing with dipole-dipole forces. But anytime that we think about dipole-dipole attraction, we need to question whether this is a special strong case where hydrogen is bound to nitrogen, oxygen, or fluorine directly. In this molecule of water, hydrogen is indeed bound directly to oxygen. Thus, the strongest force of attraction that could exist between two water molecules is the particularly strong version of the dipole-dipole attraction called hydrogen bonding, or H bonding for short. If instead two chlorine molecules get together, Cl2s, whose Lewis structures look like this, where there's no disparity in electronegativity, and thus no poles, and we're dealing with only nonpolar molecules, then the only possible intermolecular force that can exist is this London dispersion force. And so by default, must be the strongest force of attraction between these molecules of chlorine. Earlier, we looked at HF. HF molecules, again, are polar. They have dipoles because fluorine is more electronegative than hydrogen. The fluorine side is partially negatively charged, the hydrogen side partially positively charged. These dipoles align themselves in such a way that partial negative ends and partial positive ends are aligned in separate molecules. So once more, we have dipole-dipole attractions, but we've got to question whether this dipole-dipole represents a special strong case of hydrogen bonding. Is hydrogen bound to nitrogen, oxygen, or fluorine? Well, hydrogen is obviously bound directly to fluorines in both molecules. So once more, we say that hydrogen bonding represents the strongest intermolecular force of attraction between these hydrogen fluoride molecules. In our final example, if we think about two hydrogen sulfide molecules, H2S, we can consider a structure very similar to that of water. In hydrogen sulfide, we have, once more, a highly electronegative atom at the center, resulting in regions of partial positive and partial negative charge. Two hydrogen sulfide molecules might align themselves so that regions of partial positive charge and partial negative charge are aligned. So once more, we're dealing with a dipole-dipole interaction. But once more, we've got to wonder whether that dipole-dipole interaction constitutes hydrogen bonding too. So, is hydrogen bound to nitrogen, oxygen, or fluorine? In neither molecule is hydrogen bound to nitrogen, oxygen, or fluorine. It's always bound to sulfur. And if we can find just one case where hydrogen is bound to something other than nitrogen, oxygen, or fluorine, hydrogen bonding is no longer relevant, and the strongest intermolecular force of attraction defaults to dipole-dipole attraction. The concept of these intermolecular forces of attraction is important in understanding some of the phenomena associated with liquid and solid phases of material. One of the ways that we can apply intermolecular forces to thinking about the properties of liquids is to consider what happens to a beaker full of liquid that's exposed to the atmosphere at a constant temperature that's well below the boiling point, like room temperature. We expect that given enough time, eventually the particles that make up a liquid in a glass will eventually disappear. Over time, they evaporate. And this is because, statistically speaking, at the interface between where our liquid sits and the room around it, particles are in constant motion. And occasionally, that motion allows a particle to be ejected with enough force that it overcomes the intermolecular attraction that it once had to other molecules in the liquid bulk. And it can leave the nest and go off on its own incredible journey. In a sealed container, however, like in the picture on the right, if we allow a liquid's particles to leave the nest and become vapor or go off on their own incredible journey, then we could eventually imagine a situation or scenario in which we maximize the number of liquid particles that become vapor. And we would establish a balance between vapor particles and liquid particles. Because those vapor particles have nowhere to go, they just sort of become trapped in the headspace above the liquid. This balance that's reached, however, is important because once that balance is established between liquid particles and vapor particles, we can measure the pressure of that vapor. Vapor pressure is a measure of the pressure that's exerted by a liquid's vapors in a sealed container once this balance or equilibrium has been established. The higher the vapor pressure for a liquid, the more likely that liquid is to become a gas. Because the higher the vapor pressure, the more gas particles we must have, based on the same gas laws that we established in Chapter 9. We say that as a liquid vapor pressure increases, the volatility or likelihood of evaporating for that liquid increases. With increasing vapor pressure, it's much more likely that a liquid would prefer to exist in its gaseous form rather than its liquefied form. And at a given temperature, the higher the vapor pressure, the quicker a liquid will evaporate. But vapor pressure depends on two key components. For one thing, it depends on temperature. So that if we tracked a given substance's vapor pressure, like we do in this plot here, as a function of temperature, where temperature is on the x-axis and increases from left to right, what we find is that in any one of these traces, for diethyl ether, for ethanol, or for water, increasing temperature corresponds to increasing vapor pressure. Thus, as temperature goes up, vapor pressure goes up. Or intuitively, as things get hotter, they're much more likely to evaporate. The other thing that vapor pressure depends upon is the strength of intermolecular forces between molecules of a liquid. We say that as the strength of intermolecular forces increases, the vapor pressure decreases. In other words, the more strongly molecules are held together next to other molecules of the same type, the less likely they are to want to escape to become a vapor phase. Diethyl ether, plotted in orange in this graph up above, has its strongest force of intermolecular attraction as dipole-dipole. Ethanol, plotted in red, has its strongest intermolecular force of attraction as hydrogen bonding, where there's one hydrogen per ethanol molecule that can participate in hydrogen bonding. There's one hydrogen that's bound to an oxygen in ethanol. In water, plotted in blue, as we've already seen, can participate in hydrogen bonding with two hydrogens per molecule, both the hydrogens that are bound to the central oxygen atom. Clearly, the intermolecular force of attraction is strongest in water, weakest in diethyl ether. If we compare these three substances, as the strength of intermolecular forces increases at any one given temperature, like 20 degrees Celsius, as the strength of intermolecular forces increases from diethyl ether to ethanol to water, the corresponding vapor pressure has decreased. This is because increasing forces of intermolecular attraction make it less desirable for particles to want to escape their liquid phase and enter the gaseous or vapor phase. Let's discuss briefly once more the effect of temperature on vapor pressure. On the previous slide, we said that as temperature increases, we expect the vapor pressure for a liquid to increase, because increasing temperatures make it easier for individual molecules to overcome their intermolecular force of attraction to other molecules of the same type, and thus escape from the liquid phase to the gas or vapor phase. There reaches a critical point for a liquid, though, at which the temperature influences the vapor pressure enough so that the vapor pressure for a liquid becomes equal to the external atmospheric pressure. Remember, the standard atmospheric pressure is 1 atmosphere, or 760 torr, and the vapor pressure on this graph is plotted in torr. We say that the temperature at which the vapor pressure for a liquid becomes equal to the external or atmospheric pressure around that liquid is the boiling point for that liquid, the point at which it starts to spontaneously move from liquid to vapor, going through a phase change. We can estimate the normal boiling point of a substance based on a vapor pressure diagram like this graph on the right. I've highlighted on this graph 760 torr, which corresponds to 1 atmosphere standard pressure. At this pressure, the standard atmospheric pressure, we expect that the temperature at which any one of these graphs crosses 760 torr represents the boiling point for that liquid. For diethyl ether, that point is right there. For ethanol and for water, we can circle those threshold crossings. Estimating the temperature associated with each one requires us to drop a line to the x-axis. We can say that diethyl ether has a vapor pressure that crosses the normal atmospheric pressure somewhere a little more than 30. This is about 35 degrees C. Ethanol has a vapor pressure plot that crosses the 760 torr threshold at a temperature just shy of 80 degrees Celsius. This is just a little bit less than 80, about 78 degrees C. Water, meanwhile, has a graph of vapor pressure that crosses the 760 torr threshold at approximately 100 degrees Celsius. So that we expect the normal boiling point of diethyl ether to be about 35 degrees C, for ethanol about 78 degrees C, and for water about 100 degrees C. So that is effectively the bulk of this chapter. We can use intermolecular forces to describe properties of liquids and solids. Some other properties of liquids that you see on this slide include surface tension, that's the energy required to make a surface spread. Viscosity, that's the resistance of a material to flowing. And capillary action, an intermolecular force that occurs in a very narrow confined space for a fluid. You can read those definitions here on this slide, available to you on your Moodle page. Intermolecular forces also allow us to classify solids. And what's more is we can classify solid materials based upon their bonding and properties. Metallic solids consist of solely metal atoms like mercury, silver, gold, etc. These solids are often shiny, malleable, meaning we can shape them. They're conductors of heat and electricity. Ionic solids are compounds composed of cations and anions attracted to each other by opposing complete positive and negative charges. As we've seen, ionic solids typically have high melting points. They're hard and brittle and can only conduct electricity when their ions are freely mobile, when they're molten or dissolved in a solution like water. A molecular covalent solid are small molecules like H2O that form solids at very low temperatures. These things have low melting and boiling points. They're poor conductors of heat and electricity because they don't consist of ions. Network covalent solids are covalently bound molecules that have very high melting points in contrast with molecular covalent solids. They're very hard, but they're poor conductors because, again, they don't consist of cations and anions as a general rule. Things like diamond and quartz and corundum are all examples of network covalent solids, things that we've previously defined in this class. And so that rounds out our discussion of liquids and solids. We should be able to identify the strongest intermolecular force of attraction between a given set of molecules or ions. And we should be able to interpret the vapor pressure and its dependence on temperature and strength of intermolecular force. In the next chapter, we'll explore creating solutions.